Welcome to the NEB podcast, Lessons from Lab and Life. I'm your host, Lydia Morrison, and today I interview Claudia Vickers, Director of the Synthetic Biology Future Science Platform at Australia's National Research Agency, CSIRO. Professor Vickers' latest research focuses on engineering plant pathways within microbes to manufacture natural products. Throughout the pandemic, she has also focused on bringing the synthetic biology community together via an online seminar series. Hi, Claudia. Thanks so much for joining me today.
Hi, Lydia. Thanks for having me. It's a pleasure to be here.
So I was wondering if we could jump right in and you could tell us about your role at CSIRO.
Yeah, sure. So why don't I start by telling you a bit about what CSIRO is, because I guess it's an Australian institution, so maybe not everybody's heard about it before. So we're Australia's national science agency. We really have just the one large-scale science agency. We're about 5,500 people, and we have about 57 sites spread across Australia, with three or four sites internationally, including in the US. We deliver about $4.5 billion a year to the Australian economy through science and technology. So we're really industry facing rather than academic facing. We're a really big and diverse research organisation. So we work on everything from synthetic biology, where I am, to space science and everything in between. Nothing is sort of off the board for us. And we really deliver to the needs of Australian industry. So very innovation orientated. We're the largest patent holder in Australia, and very partner orientated. So we've got about 2,500 partners, but we also deliver into the secondary school and primary school teaching systems and university systems by taking on PhD students and undergrads for internships and postdoctoral studies. And we reach about 150,000 school kids a year through those programs as well. So pretty diverse organisation. So my role...
That's amazing.
Yeah, it is. And it's really exciting to be part of an organisation that's so interdisciplinary, because you can really build science at the nexus of those different disciplines. And that's what synthetic biology is really about. So my role is as director of a program called a Future Science Platform in synthetic biology. Future Science platforms are Horizon 3 science, so they're far from the pointy end of translation, but they're new areas that Australia needs to develop strategically and are considered to be important for our future, our research future, and our industry-facing development. So the Future Science Platform in synthetic biology is obviously about developing synthetic biology. There are two key missions of that program. One is to build a collaborative research capability across the whole nation, so not just inside CSIRO, but with university and research institute partners as well. And the second one is to build a synthetic biology-enabled industry in the country. So they're quite large, lofty objectives, of course. We've been going now for about 4 years. We're about a $60 million program. We have about 250 people involved in the program. We've trained about 90 early to mid-career researchers from PhD level all the way through to young scientist level, mid-career level. We have about 100 projects at any one time going through the program. And we're highly collaborative. So we have about 45 partners nationally, internationally, very well internationally networked. We've established really important infrastructure, so a high throughput DNA and organism engineering facility called a biofoundry, which I can tell you about if you're interested later on. And we've done a lot of workshops, training programs, and education programs. We do a lot of policy input work, so we feed into national and international policy at various different levels. And we work across both biophysical and social sciences. So the program is really a melding of biophysical and social sciences in that space. It's a really exciting place to be in, and it's a lot of fun. So that's why it's important to me. I think it's really critical in terms of Australia's research capability internationally and our ability to really drive impact.
Absolutely. So was the past year of the pandemic particularly tough in terms of building that future of synthetic biology program within Australia, or what efforts have you been making in the past year to sort of continue the drive forward?
So in Australia, I think in many ways we've been very fortunate compared to the rest of the world, because we're an island nation a long way from anywhere else, and it was relatively easy to close our borders and go for an elimination strategy for coronavirus. And we really have had very little impact in terms of mortality. We have had some long lockdowns that have been difficult, but it hasn't cost us in terms of lives the way it has cost other people. It's definitely cost livelihoods. In terms of our research program, so we spent a lot of time reaching out to find out what sort of support we could provide, and often it was no cost extensions to take into account interrupted programs for our early mid-career researchers and such forth. Some people have been out of the lab. Most people were able to manage their projects so that they could still be productive during that time when they were out of the lab. And then once we come out of lockdown, so for us up here in Brisbane, we had a few months of lockdown and then went back to life, and we have snap lockdowns occasionally. So I think relative to the rest of the world, I have many international friends who have been literally out of the lab for a year. We haven't had such a bad impact, but we've been able to support our people most of the time through those pandemic-inflicted delays.
Absolutely. And in order to continue to build a community of synthetic biologists within Australia, have you all been meeting online during this time, or have you been able to meet in person?
Yeah, absolutely. So we've started online seminar series, which has been really fantastic. And in fact, with an online seminar series, you can reach a lot more people than you can reach with a local seminar series. So that's been wonderful, and I think it's given great opportunities to people. We really have shifted online for almost everything. So prior to pandemic, I was probably traveling 3 to 4 months of the year away from my home city, and that was nationally and internationally. And now I'm not traveling at all, but I'm still doing almost everything I would otherwise do, apart from the in-person conferences. So the online platforms are really good. In Australia, it actually makes it very accessible, because a lot of the things that happen internationally are more difficult to get to because we're so far away from everything. The only downside is that a lot of it happens in the middle of the night, so it can be a bit challenging in terms of time zones.
Absolutely, much like this interview. I wanted to shift focus a little bit and talk specifically about your research. I read that your research focuses on engineering plant pathways within plants and microbes in order to manufacture natural products. Could you tell me more about that work?
Yeah, sure. So I'm a plant molecular biologist by training, and I spent probably a decade working on engineering in plants and using my engineering skills to better understand plant physiology and stress responses. And during that time, I was working in a class of natural products called isoprenoids. So these isoprenoids are really fascinating, and they're a really large family of natural products. And they include small volatile molecules and long complex molecules that are heavily decorated. And they have roles in membrane stabilization, in volatile messaging between plants and between plants and insects. They are attractants for pollinators. They're many of the colors and the flavors that come from the food that we eat come from the isoprenoid molecules in them. So carotenoids, your reds and your yellows and oranges. So these are all in the isoprenoid family. And I was interested in those because there's a molecule called Isoprene, which is a 5-carbon hydrocarbon, so very small. It's volatile and it's emitted by plants, and it's emitted in teragram amounts per annum into the atmosphere from the biota. And the question is, this is an enormous amount of carbon going into the atmosphere, and it's so isoprene isn't a greenhouse gas per se, but it interacts with other gases in the atmosphere that would otherwise soak up greenhouse gases and increases the residence time of greenhouse gases. So it's really important in global atmospheric biogeochemical cycles. But we didn't really understand properly why plants made that molecule. So I was interested in understanding better the physiology around that. And it turns out that it's basically part of their stress response system. It interacts with their antioxidant metabolism and helps them deal with oxidative stresses. So that was the piece of work that I was doing to learn about isoprenoids and start working in that space. Then when I came back to Australia, I became interested in this metabolic engineering thing. And metabolic engineering is essentially redesigning, in this case, microbes and their metabolism to channel carbon from the feedstock that you give to them all the way through to the product that you're interested in them making that has an industrial application. And it turns out that isoprenoids have many, many different industrial applications. They're such a large and chemically complex and diverse group of natural products that they have many different applications. So they range from pharmaceuticals through to flavors and fragrances, food additives, colorants, cosmetic ingredients, solvents, monomers that can be made into polymers to make rubbers and fibers, and all the way up to very high volume, low value products like biofuels. So we have a whole range of things that we can make.
That's amazing. So what has the success been like in reprogramming microbes to produce these?
Yeah, so we've done quite a lot of work on this. There are two different pathways that are involved in producing these. In yeast, it's the mevalonic pathway, which is a pathway that's found in us as well. So it's quite interesting to study from a physiological point of view and for a lot of different applications. So what we have found is that isoprenoids exist in different classes that are related to the number of carbon molecules in their isoprenoid tail. And some of them are really challenging to get to. And so we've had to develop mechanisms to bypass or redirect carbon at specific nodes in the isoprenoid pathway. So we can make either 5 carbon or 10 carbon or 15 carbon compounds. And we found that using protein degradation as a metabolic engineering tool instead of trying to upregulate or downregulate at the transcriptional level was really successful, particularly where you're dealing with a protein that is essential, so you can't just knock it out, or that's very stable, so transcription knockdown isn't very effective. So that's a tool that we've used to really successfully redirect metabolic flux to various nodes in the isoprenoid pathway, and that's delivered gram per liter titers, tens of grams per liter of the products that we're interested in, which is essentially industrial level for a mid-level chemical, so a solvent or a polymer. And we're really excited by that because that's real-world impact.
Absolutely. And so you mentioned that you can produce 5 carbon, 10 carbon, 15 carbon. Is there a reason that you're producing these multiples of 5s?
Really good question. It's called the Isoprene rule, and I'm not going to try and pronounce the name of the guy I think it's Rudishka, who came up with the Isoprene rule. So the reason is because at the bottom end of the metabolic pathway that makes isoprenoids, the mevalonic pathway or the other pathway, it makes 5 carbon prenyl phosphates called isopentenyl pyrophosphate and dimethyl allyl pyrophosphate. And they're isomers. And they're 5 carbon units, and you use them just like Lego building blocks, which is a beautiful analogy for the way synthetic biology works, to add one unit and another unit and another unit. And that's why you have 5, 10, 15, 20 carbon, etc. modular isoprenoid compounds. There are others that you can take individual carbons away and get different carbon numbers, but that's the basic background of why they're modular like that.
That's interesting. I love the simplicity in nature that turns up in even the most complex scientific processes.
Yeah, it is, and it's actually, I think, unusual in nature. So the basic tenet behind synthetic biology is that we can treat biological systems almost like integrated circuits, and we can modularize the DNA encoded component tree and build it up into more and more complex systems. And it works fine, but of course, biology is mutable and it evolves. So it's not quite as simple as working with an electronic circuit board, but it's really more about the philosophy that sits around that. Using design, build, test, learning cycles that are iterative, using high throughput engineering, modularized engineering approaches and components that you can build up in a more and more complex way.
Yeah, and I think what you're describing is really the basis of synthetic biology, right?
Yeah, and that basically allows you to engineer the biology in a more precise and sophisticated and much more rapid way to get to a solution to whatever problem you're trying to solve more quickly.
I think it's a great application of sort of the theories of computer science and electronic programming to biology, and it's amazing how similar the two systems can actually be.
Yeah, and the thing about this is that it's truly interdisciplinary. So it's blending of biological engineering with automation and robotics and artificial intelligence for dealing with big data sets. And to do that, there's not that many places that allow you to access all that capability under one roof. And CSIRO is obviously ideal for that because it's such a broad organization.
Yeah, another example of how the integration of multiple scientific disciplines, but even beyond scientific disciplines into different areas of study in general, can really be beneficial in terms of moving science and understanding forward.
Yes, very much so.
So where do you see synthetic biology heading in the future?
Well, I mean, I think the cutting edge of synthetic biology now is that nexus of big data and artificial intelligence and bioengineering, of course. And we're really just starting to explore into those spaces. We haven't really cracked the question of how do we get artificial intelligence algorithms to suggest the next step as opposed to just deal with and assess all the data and information. So how do we feed it into that design, build, test, learn cycle? So that's one of the areas that we're working in at the moment. And in terms of, where are the next Horizon 3 science questions, exploring into that space, I think, is really very exciting.
Yeah, absolutely. Lastly, I was just wondering if you have any sort of stories about something good or inspirational that's happened in your life or in your research since the pandemic began.
Well, the immediate good thing is not traveling so much. For me, whilst that might sound weird to some people, for me it's really great to be able to actually sit at home and focus for long periods of time without having to be up and off and around the world and on to the next thing. And it's meant I've spent a lot more time with my family on a day-to-day basis. So I have two small kids, they're 9 and 6, and they miss me a lot when I'm traveling. So it's a challenge always to be in a position that's relatively senior and involves a lot of travel away from home. And when you're doing that with little children, then that's a challenge as well. But it's been a lot easier in that period of time from that perspective. So that's my good story.
Yeah, I think that's wonderful. And I think that that's probably a lot of people's good stories, I think that one of the lessons that's come out of the pandemic is that, we can collaborate globally and communicate. We can do all that, from the comfort of our own home with the technological advances that we have available to us today. And certainly some of those interactions aren't exactly the same as they might be face to face. But I think that the pandemic has taught us that we're actually capable of doing a lot more remotely and still making important connections remotely, where we used to feel like we needed to be in person for those interactions.
Yes, I think that going forward, the global carbon footprint of the scientific community will probably decrease. Nothing can replace those personal interactions, but we can do a lot, and we can probably do those less frequently and still get good value out of it.
Absolutely. Thank you so much for joining me today, Claudia.
Thanks, Lydia. A pleasure.
Thanks for listening to this episode of the NEB podcast. Join us next time when I interview plant geneticist Kate Creasy, president and founder of the Grow More Foundation, whose mission is to help end world hunger by bringing synthetic biology tools to developing countries and enabling communities to grow more fruitful crops.